Today, we are going to discuss quantum support vector machines. Support vector machines are one of the main classification mechanism in classical machine learning. And today we will discuss its extension to quantum machine learning. And what I will do that I will go over the formulation of support vector machines quickly, and then I will discuss, how it's implemented in classical and quantum machine learning algorithms. And at the end, again, we will go through a couple of notebooks where I will explain its implementation for a toy data set and for a practical data set. So let me begin by sharing my screen. Okay, so let's start with what support vector machines are. And I'm going to uh, derive the cost function for support vector machine, and in the way I will also explain. And I have, learned many classical the machine learning algorithms and also quantum machine learning algorithms as well. But I have never found a more elegant, formulation and a more elegant classification mechanism than support vector machines. I'm talking aesthetically, not in terms of accuracy or anything. So let me walk you through its derivation because it sort of is very ingenuine, I must say. So the problem at hand is this. So let me start by going through the support vector machine theory in a nutshell, or the main thing, in which let's think about, let's say, a data set that is composed of two types of points. So maybe x is -1 and O is +1. And our goal is to find a, uh, a hyperplane that separates these two data sets into two sets. So for example, we can think about a hyperplane like this, or maybe like this, or maybe like this. So the question is that which one would be better in terms of predicting the new data points? And that this question is answered in this way that that separator is the best, which has the maximum separation or maximum margin from the nearest data points on the in both data sets. So let me explain what I mean. For example, actually, let's just remove few more data points to make some space. So suppose we have data points like this. So let's imagine a separator like this. And this is sort of a boundary on this side, and this is a sort of a boundary on this side. And this separator, let's say this has a functional form f theta of x as some theta dot x, and let's assume that the bias is 0. So I'm taking b0 for now. And suppose the distance of this plane from this side is delta, and similarly, it's the same distance from the other side. So it's like in the middle of the region between the two. And we want to find a separator or a hyperplane which makes this delta maximum. So like we are looking for a plane such that it has maximum margin. That is, it's maximally far away from the data sets on both sides. Okay, so let's see what is a cost function that is that we have to minimize to find this plane that separates the data point. So for this purpose, let's say that suppose this is the side of the point in which f theta is greater than 0, and this is the side of the point in which f theta is negative. So these are the labels, by the way, with +1 y, and these are the label with -1 y. So the label is -1 here, and the label is +1 on the other side. So assume that they lie on the positive side of the plane, and these points lie on the other side of the plane. Let me see, is there a question in the chat? Why a maximum margin is better for prediction? Because it reduces the prediction error. If, for example, suppose I take this one as the separator. So then when a new data point comes in, suppose it comes here or it comes here, there's a very high probability of misclassification if it has a label -1. So that's why we want the separator as far away from both data sets as possible, so that the new data point, when it comes, it can be predicted with more accuracy. Okay, so let's say, let me see if there's another question. Okay, perfect. So let's think of this point, and suppose this is some origin on this separator. I'm taking by 0, so it means that the origin is somewhere on this line for the sake of easiness. Suppose that uh, the data vector for this point is some xs. So we call it support vector, and we'll see later on why it's called a support vector. So like in general, the data point is x, and suppose the data point uh, that lies on this sort of margin is xs. And I can easily write this xs vector as sum of two vectors. So this xs can be written as x parallel plus x perpendicular, where this is x perpendicular and this part of the vector is x parallel. So this xs vector is sum of these two vectors. And since if the equation of this plane is this, we know from geometry that if I make a vector theta, which is just a vector of these weights, let's say there are n weights, then this theta vector is the normal to this plane. Okay, so it means I can find a unit vector perpendicular to the plane by just dividing this vector with its magnitude. So it means I can write this support vector like this: the parallel component parallel to the plane, and the component perpendicular to the plane. And the component perpendicular to the plane is like this. This delta is the magnitude of this vector, and this theta vector over theta is the unit vector along this direction. So it means that the equation, the function for the support vector then becomes theta dot xs, and if I substitute the value of xs, it becomes theta dot x parallel plus delta is a scalar, so theta dot over theta, and We know that since this theta is perpendicular to the plane, this is the theta vector, and this x parallel is parallel, so this dot product is 0. And this theta dot theta is nothing but theta square. So one theta cancels below, so this becomes delta theta. So f theta of xs is this, which means that delta is now, which is the margin f theta of xs over theta, where this theta is the magnitude of our parameter vector, okay, the parameters that define our model. So it means to have this delta maximum, what we need is to maximize delta. We can minimize theta, or even better yet, we need to minimize. If we can do, both things together, so we can maximize this and we can minimize this. So essentially we want to minimize this thing, so this thing must be minimized. There's a question, and how do we come to know that theta is perpendicular to the plane? This is a simple fact from geometry. If you write the equation of any plane, then this vector is, normal. For example, let's say there's a digression. So the equation of a line is equal to, you know, uh, some f of theta is something like, let's say, theta 1 x1 plus theta 2 x2. And so let's say this is x1, this is x2, and this is the equation of this line. And we can see that this theta 1 and theta 2, if we make a vector with this vector will be perpendicular to this thing. Okay, so let's come back here, that we have to minimize this thing to get the maximum margin. And there is a constraint as well. The constraint is this. What's the constraint? Constraint that our data points, the all the data points, they should have this positive, and actually they should be bigger than delta when y is +1, and our points with the negative labels, they must, their f theta of x must be less than delta. So coming back here to the data, so for all of this point, when I substitute them in my model f theta of x, they should have a positive value greater than delta, that they should all lie on this side of uh, this classifier and be a distance delta away. And similarly, these points, they are lying on the negative side of the plane. This is the plane that is separating. Okay, so this plane is separating the data into two sets with this margin. So for this these points with label -1, this function not only should be less than 0, it should be even less than delta on this side. So this means actually greater than 0, this should be put minus delta. So this actually means that if and if you look at this thing, actually from this thing, if I multiply y and f theta together, suppose, so let's make it for one point. So for any given point, yi f theta of xi is greater than delta, because this is positive number, this is positive, so product is positive. And now let's see for this thing. So this is a negative number, and its product with this thing should be this, and you multiply with minus sign, this gets flipped. So this should like this. So it means that for both types of points, whether yi is minus or plus, the product of yi and this thing should be greater than delta, which means that constraint for each point translates to yi f theta of xi minus delta should be this. So this is sort of a constrained optimization. The bigger this is than delta, the better it is. So it means the cost function is now something like this. So the cost function of as function of theta, we have to minimize theta over delta. And to minimize, instead of minimizing theta over delta, it's better to minimize theta over delta square. And actually, let's just put a factor of out. This is just, easier because if this is smaller, theta is smaller, theta over delta is smaller anyway. But with this square, the square root in theta goes away, so the derivatives become easier. Remember, theta is theta square is theta 1 square, theta 2 square all the way to theta n square. And then there is a constraint as well. So we have to minimize this and we have to maximize this with this constraint equation. So to maximize this, I can actually minimize the negative of this. So let me put a minus sign. And then the constraint optimization actually leads to an equation that's from Lagrange's method, that we have a function to minimize, and then the constraints, they come with the what we call Lagrange parameter or Lagrange multiplier. So this goes in here like this. So this is the function that we have to now minimize. This a little bit over here. So okay, so this is the main cost function. And we can actually rewrite it in another way as well. So let's just write it half theta over delta square minus I 1 to m lambda I. And let's take this delta common. So I'm taking delta out. And let's write the expression for f theta. So this was nothing but theta dot xi. And actually, let's put this I on top, because this is the x vector for ith example, and there is a delta here minus 1. So I took the delta common, so delta is here, and since there is no delta here, a delta appears in the denominator over here. So let's make a little bit of a substitution. Let's say this delta theta is some theta prime, and let's call some this alpha delta some alpha prime. So this cost function essentially become cost function theta prime. So this is like theta prime square over 2 minus I alpha prime yi theta dot xi minus 1. So this is essentially rescaling our parameters. Okay. And since these are Lagrange constants that we have to find anyway, so instead of finding Lagrange constant, we can, find lambda I delta I, because they are just appearing in product. So this is the form of the cost function that you will mostly see in the literature. Now, if the cost function was only this, then there was no magic in it. It wasn't, it wouldn't be this famous, this method, if the cost function was just like this, because this is like a usual way of writing. We are trying to find these parameters, and, this is our cost function. We are minimizing this function subject to these constraints. But the beauty of support vector machines is this, that in a dual form, this lends itself to another way of optimizing this problem, that give rise to new methods and new possibilities for machine learning scientists. And that is called a dual form, which is actually really easy to get. All we have to do is notice that to find these, parameters theta, uh, we have to make sure that partial C by partial theta prime is just zero. So, and because this is the requirement for these parameters that at a minima, the derivative of the cost function would be zero. And if I find the derivative of this equation, this becomes, uh, so this theta prime, just remember, this is theta 1 square plus theta 2 square plus theta 3 square and so on. So for the, let's actually write j. So for the jth derivative, this would become simply theta j, okay? And then minus, and just to show, because some people might, be confused that why this is. So theta 1 square, theta 2 square, and so on. So for the jth theta, all other derivatives are going to be zero. For example, j is equal to 2. So only this derivative survives, which is 2 theta 2. And since there's a 2 over here, so that 2 cancels and I'm just left with theta 2. So if the j is 10, so I'm just left with theta 10. Okay, so this derivative is this, and the derivative over here is a little bit tricky. I alpha I prime. And when I take the derivative of this part, yi is just as it is. And then remember this theta dot x is an inner product, okay? Inner product between theta and dot x. So when I take its derivatives of the theta j, I'm only left with the theta uh, prime j. And over here, we will have only the x j. So the jth part survives, and the derivative of -1 is 0. So we are left with this thing. So this means that theta j is equal to I alpha I prime yi theta j prime xj I. And now this is for theta, and so this would be true for each j, which means that the full theta vector would just be I alpha I yi. So I have the same equation for each theta j. So the same equation for the full theta dot x. So we have the same equation for any j theta. So for the full vector, we'll have an equation like this. And now if I substitute this value of theta back in this cost function, what do I get? So let's substitute it here. So I'm going to substitute for this as well. So cost function as a function of theta and alphas. Let me just write it again actually. So there was theta square. So that theta square can be written as theta transpose into theta, because that's how we can get theta square. And then minus was I alpha I yi theta. And the theta dot can simply be written as theta transpose into, xi minus 1. So now let's substitute this theta in here. So this becomes C. Actually, theta will simply go away because we are just putting this theta here. So this becomes half. So for this theta, we take its transpose, I alpha I prime, yi theta I dot xi, and okay, let me see, there is an issue that I can see easily, that this theta j is mm, okay, so this theta j actually should not be appearing here. We made an error over here because if you look over here, so this part is theta, let me just put with red color. So this was theta 1 x1, theta 2 x2, and so on. So if I take the derivative with respect to theta j, I should only get xj, and this, theta, its derivative would be 1. So this should not be here, and which means that this is not going to be here. So this is also not here, and substituting. So everybody's okay with this thing? Because here, sorry, going too fast. So when we were taking the derivatives here, it was theta square. So that's why the derivative yielded theta. And here there is only a theta. So when we find its derivative, this is gone and only its coefficient xj is left. All right. So this theta is this. And when I substitute this alpha I yi x transpose. And then for this theta, we get, let me use another index, j, alpha j, and yj, and xj, minus the second term. And for this, let's put the value of this theta. So this becomes, again, I, alpha I, yi, and for theta, we put, let's use j now, alpha j, yj, and xj transpose. And there's a, so it's transpose, so I don't have to put the dot because let's put a dot just to make sure there's a dot product. So even if we don't put it, then it's clear, but just to be sure. And then there is this term alpha I multiplying with -1. So this becomes plus I alpha I. All right. So now you see this term, and this, they're exactly the same, except that this is half, this is -1. So what we get is I, alpha I, this term, and then minus half I, j. There are two sums, so let me combine them. So alpha I, alpha j, yi, yj, and then there is this xj transpose dot xi. So now this cost only depends on the Lagrange multipliers alphas. And there's another very important thing that has happened, that it depends on our data points, but not directly. It only depends on their dot product. So this is the jth vector, xj, and this is the ith vector. So this is actually the main advantage of writing it in this form, that we are optimizing now, first of all, for Lagrange multiplier and not the parameters of the model. Okay, we can get the model from this once we have these alphas, but we are now optimizing a model in terms of its Lagrange parameter of the cost function and not directly the parameters. And this cost function only requires the inner product of the data points, all of the data points, instead of the data points as it is. So this gives rise to what we call kernel methods. That if we have a data set that is not separable, let's say linearly in one space, we can go to another space, suppose, by a transformation to a new set of coordinates. Let me call them some y vector, which is just the function of x vector, and they don't have necessarily the same dimension. Usually y is higher dimensional. The advantage of this support vector machine formalism is this, that in this, so this is, let's say, y1, y2, y3 space, and this is x1, x2. So in this new space, we don't have to compute this feature transformation. All we need is this inner product between the jth vector and the ith vector. So if we find a map in which we are, let's say, going to very high dimensional space, we don't need to find out these vectors if we can just compute the inner product directly. So it means that our cost function in another space is simply alpha I. I'm just forgetting these primes again. It doesn't really matter at all what you call them, but let's keep them. So all we need is this new inner product yt j dot yi, and this thing, let's call it some kernel, which is just the inner product in the higher dimensional space corresponding to these two data points. So all we have to do is j I is compute this inner product between the two vectors. And if we are lucky and we apology, this is sometime goes too fast up and down. All right, so let me actually stop and see if there are any questions. So the advantage of using this support vector formalism is clear. Thank you, Fatma. So I hope it's clear to everybody else as well. Let's now see where the quantumness comes in. So classically, let's say our x vector is 10 dimensional, and the data is all jumbled up, and we might have to go to like maybe 20 dimensional vector y to be able to separate it, or maybe even higher, maybe 100 dimensional. So when we go to higher and higher dimension, find finding this inner product may not always be easy, because there are only few choices in classical machine learning where we get kernels that are easy to compute. Because in classical machine learning, people always try to find a kernel, find a k such that it's easy to compute without having to compute this transformation y is equal to f of x. Nobody wants to do this because this is not needed. So if you are going to 100 dimensional space and you're working out this transformation all the time, then the computation cost is too high. And for an example is, for example, an exponential kernel. So an exponential kernel takes you to an exponential space. For example, a single x maybe can be mapped to a Gaussian feature space, where this x might be the mean in the new space. So let's say this is y. And then the inner product of two Gaussian function, it's really easy to compute without having to compute each of this point in the transformation. So you have to look for a kernel, a transformation for which you can compute kernel without having to compute this transformation to go to a higher dimensional space. However, in the quantum machine learning gives us an advantage because we can go to a higher dimensional Hilbert space without doing too many calculations. For example, with 10 qubits, we can go to a 10 dimensional Hilbert space. However, there is a difference in quantum machine learning. In QML, we always implement this transformation. Let's call it some phi of x. We implement this instead of looking for a kernel where we just directly compute the inner product. So we actually implement this transformation, and from this transformation we compute this kernel. And let me first show how to compute the kernel for a given transformation. Then I'll give a few examples of these kernels. So this transformation is really easy to implement because all I have to do is to transform any data to a higher dimensional space. I will have to come up with some data encoding technique and apply this unitary operator to an initial state, and then I get a state. So for example, this could be an amplitude encoding, a ZZ feature map, a poly feature map, and so on. So this can be our angle encoding, any encoding that you can think of. So all these encoding essentially implement these transformations. And how do we compute this kernel? So that kernel means that I have to compute this inner product of, let's say, between a data point xj and a data point xi. So this is really easy to compute because this phi of xj is nothing but s dagger of xj, and on this side I have x of this xj xi 0. So it means that I can start from a zero state, implement s of xi. So let's say there is some encoding block, a unitary s that is encoding some ith data point. And then since you see this is 0, so let me just explain it again. So 0 s dagger xj s xi 0. So if I look at this thing, so from 0 state I apply this s of xi, and after this I apply this next operator, which is the dagger of this circuit, and it's encoding another data vector xj, not this one. And then at the output, I just do measurements. And of course, when I do, let's say, z measurement, I get uh, a bar chart like this, and so on. So there might be, other terms. All I do is take this thing and this, how many times I got the 0, and I compute the probability of 0 by, this number that I got 0 and divided by total number. So I get this probability because this is nothing but the probability of getting 0. So we can compute this kernel by implementing a feature transformation here and the inverse of feature transformation for another point over here. And you can easily see that if xi and xj are the same, since this is s dagger, this product should be unitary. So I should get 1 if I have both points the same. So our kernel matrix would be looking something like this: 1, 1, 1, 1, 1, 1, and some, numbers over here. Not zeros in general, but other numbers. But the diagonal, we will always have 1. And sometimes we don't actually even compute it, we just put 1 instead of computing it. Okay, so let's now talk about how to implement this quantum support vector machine in code. So to implement, choose a feature map phi of x, compute kernel matrix by computing the probability of getting 0 for all combination of the data points. Suppose you have 20 points in your training set. So all you will have to compute 400 entries, because you xi is first point, and then xj have to loop all the way from 1 to 20. Then xi is 2, and then xj will have to loop again 1 to 20, and so on. So there are 400 possible combinations. So this matrix would be 20 by 20 if you have 20 examples in the training sets. And when you have to want to do the prediction, you will need to compute the inner product of each element in the test set with each element in the training set. So after you compute this k, you train the SVM. And then this SVM code is just the code whether you use classical machine learning or quantum machine learning, because the difference in classical and quantum is not the cost function. The cost function is exactly the same. There is only one difference, that how do you implement this feature transformation. So whether you go to a higher dimensional space uh, from X to Y through a classical transformation or through a quantum transformation. And that is just impacting this part. So in the classical SVM and in quantum SVM, the only difference is that how this kernel matrix is computed. So once kernel matrix has been computed, we just go to a classical computer and implement the state vector machine, the optimization problem. Any questions? All right, so let's now take a few examples of quantum feature maps. Just a quick before we go through the code. Suppose we take basis encoding. So basis encoding, if you remember, it encodes the X as maybe some binary number. So our state psi of X is just this binary state. And suppose there is another vector Y. Right now, let me take this Xi as some X and Xj as some Y vector. That will just make the life a little bit easier. So psi of Y would be similarly a binary state encoded like this. So what's going to be the kernel for this feature map? The kernel is the inner product of these two states. And we can easily see the inner product would always be 0 if x is not equal to y, and will always be 1 if x is equal to y. Because these binary states in quantum mechanics, they're orthogonal. They form, orthogonal basis of a Hilbert space. So whenever there is even a difference of 1 bit in these two, the inner product will be 0. Because this inner product between these two states is essentially the inner product between each individual state. So x0, y0. So even if one of the inner product is 0, the product will be 0. So it means this basis encoding actually provide a trivial feature map in quantum machine learning. So this is actually a nice way of getting intuition about various encoding schemes as well, that what they're actually doing. So they are giving rise to a kernel which doesn't essentially do any transformation at all. So let's see what amplitude encoding does. So in amplitude encoding, a state psi of x is encoded as like this, x1. So let's call it x0, 0, x1, 1, x2, 2, all the way to, whatever number of features we have. So similarly, a y vector would be translated like this. So what's the inner product between this? So what's the kernel matrix entries? Or what is the feature map? So it's just when you take the inner product, we get x naught, y naught, x1, y1, x2, y2, all the way to x and y. So this is essentially a polynomial map. So it's a polynomial transformation. And polynomial transformation is also classically easy. So it means amplitude encoding leads to a state vector machine that can also be implemented classically efficiently. Similarly, you can, think about the product state. So in all the product states, they lead to classically efficient kernel methods anyway, but you can work out what kernel they transform to. Let's talk about one particular technique, the ZZ feature map. So the ZZ feature map was essentially a map like this. If you recall that there was a Hadamard gate, there was a phase gate, there was a Hadamard gate, there was a phase gate. This depended on X1, X2, and so on. So, and then there was this, ZZ gate that depended on, X1, X2, and other things. So, and if I, call whatever this is some V phi. So this V phi is nothing but a vector that can be generated from some function like this. So this is this Z rotation generation. Okay, there's only a single Z operator times some ij, and there is a function that depends on no I and j two coordinate, and then there was a zi cj. So it's a map like this. And if you want to find out what kind of kernel it is, you will have to implement this v phi of some x and then implement its dagger. Iska dagger kya hoga? Its dagger would be the dagger of this circuit. So v phi y and then the Hadamard later. Remember, when you take dagger, the operator's order change. So A B dagger is B dagger A dagger. because there's a transpose inside the dagger. And this, you can write this, and you can see from here that it's almost like an exponential kernel. And it's not uh, efficiently computable on a classical computer directly, but it can be estimated to within a reasonable tolerance very well. However, if you have two repetition for this circuit, so let's say V5X, Hadamard V5X. So this is like one feature map. And then for kernel, you will have to take its dagger, which would be V5Y, Hadamard, dagger, continuing here, V5Y, dagger. So this circuit is actually known to be classically hard to compute. And this is n bit, it's not a single bit. And this gave rise to a kernel that has been found to be efficient in some problem like discrete logarithm and other data sets. However, in general, the identification of a kernel is actually a very hard problem. And there really is no way to know how to select a feature map for your data that give rise to that can solve your problem and that can do better than classical as well. So generally what we do, we start with a simple map, and then people would add untangling layer to see if it can work better than the simple one, and maybe you can add repetitions and then keep experimenting, and at the end of the day you might come up with a kernel that classifies your data very well and maybe better than classical. And sometime what we can actually do, we can have trainable parameters inside the kernel as well. Okay. And then this theta is treated as like a hyperparameter. You train yours, you classify your data for various values of theta and see that what value of parameter gives you the highest accuracy. So you just, keep that kernel. So this method is sometimes called kernel alignment, that we have a trainable parameter inside the kernel as well. So which essentially combines the kernel matrix method or the support vector machine method with the quantum variational circuit optimization routines. So let me stop here and